Today we are going to discuss on a very important topic, and that is regarding injection of hydrogenous gases into blast furnace Tuyeres for reducing CO₂ emission. The question arises that why this important? As you must be knowing, the blast furnace is still the workhorse of global steel production. There is no doubt about it, and also its biggest emitter of CO₂. Even with the rise of hydrogen-based DRI and EAF routes, more than 80%, around 80% of the world iron in 2030 will still be made in blast furnaces. According to the International Energy Agency, now this review dives deep into how injecting hydrogen-rich gases like natural gas, coke oven gas, and pure hydrogen through the year can significantly reduce CO₂ emission, replace coke, and improve furnace operations. Now, this presentation is unique. That doesn't just summarize the past studies, it compares modeling data, real world plant trials, and even introduces a validated ID zonal model to explain how heat transfer, gas flow, and reduction reactions behave under different injection conditions. In short, it's the most comprehensive summary we have so far on hydrogenous gas injection for blast furnace decarbonization. So before we talk about hydrogen gas injection, let's quickly understand the big picture. Steel production is responsible for nearly 8% of world's CO₂ emissions, and most of that comes from blast furnace, which still dominate the industry. While there is a strong push towards hydrogen based DRI and electric arc furnaces route. Projects like hybrid and S2 green steel, their full scale rollout will take time. Why? Because green hydrogen is still limited, and DRI grade O's with over 67% iron content are not widely available. According to the International Energy Agency, even in 2030, blast furnace will still account for around 80% of the world iron production. That's why this review paper focuses on what we can do now to reduce emission in existing blast furnaces without waiting for complete infrastructure transformation. And one of the most promising interim solutions, injecting hydrogen rich gases like natural gas, coke oven gas, or even pure hydrogen directly into the Tuyeres zone. Let's now break down the main gases being explored for Tuyeres injection into blast furnace. First, we have natural gas, primarily methane, which has been used for decades in various plants. It's rich in both hydrogen and carbon, offering high heat and decent coke replacement. Next is coke oven gas or COG. This is a byproduct of coking processes already available in integrated steel plants. It contains a high percentage of hydrogen, about 55%, along with carbon monoxide and a small amount of methane. And finally, we have pure hydrogen, either injected cold or preheated to temperature close to the blast furnace, such as 1200 degrees centigrade or even 1250 degrees centigrade. These gases are called hydrogenous because they contain hydrogen and act as reducing agents. When injected properly, they can replace coke, lower direct CO2 generation, and still drive the necessary reduction of iron oxides. Each gas offered different advantages and limitations, and as we all see next, their performances varies across modeling, experiments, and industry data. Now, let's begin with the natural gas. Historically, the most widely used hydrogenous gas of blast furnace injection. Natural gas, primarily made of methane, cracks into hydrogen and carbon monoxide in the raceway. These gases contribute to reducing iron oxide, replacing part of the coke. Industrial data from Ukraine, Egypt, and the US shows that injecting 70 to 100 cubic meters per ton of hot metal can achieve a coke replacement ratio between zero point 0.7 and 1.1 kg per cubic meter. That's a substantial reduction. CO2 emissions can be cut by 0.07 to 0.10% per normal meter cube of natural gas injected, making it the most effective among hydrogenous gases in terms of total CO2 impact. However, there are challenges, mainly the drop in raceway adiabatic flame temperature, which can destabilize the smelting. Also, unconverted methane can lead to chute formation, which may block gas passages, affect slag flow, or even clog scrubbers. Model shows that adjusting oxygen enrichment and blast temperature is key to maintaining balance between gas heat Wg and material heat Wm, a relationship we all see repeatedly for all gases discussed. Next is coke oven gas or COG, a hydrogen rich byproduct gas produced in the coking process. It's being used in blast furnaces for decades, especially in integrated steel plants. What makes COG appealing is its high hydrogen content, around 55% as we earlier pronounced, and the fact that it contains a far fewer complex hydrocarbons than natural gas. This means it converts more cleanly in the raceway and contribute significantly to indirect reduction of iron oxides. Injection rate typically range from 50 to 100 cubic meter per ton of hot metal with a coke replacement ratio of 0.4 to 0.49 kg per meter cube. While the CRR is lower than natural gas, the CO2 reduction potential remain comparable in the range of 0.04 to 0.06% per cubic meter injected because COG contain less carbon. However, a key limitation is availability. COG is already used for stoves, reheating furnaces, and power generation inside the plant, making it a competing energy source. Also, excessive oxygen enrichment or injection rates can reduce top gas temperature and disturb the thermal balance. So optimization is critical. Now let's talk about pure hydrogen injection, the most direct path to decarbonizing the blast furnace. Unlike natural gas or COG, pure hydrogen is a zero carbon reductant, meaning any hydrogen used directly reduces iron oxide without adding CO2. Industrial trials have taken place at ThyssenKrupp, Tata Steel, and recently at Cleveland Cliffs. Experimental studies in Japan under the Course 50 project tested injection rates up to 359 meter cube per ton hot metal, achieving a 17% reduction in carbon use and 33% drop in CO2 emissions when preheated hydrogen was used. Under cold condition, CRRs are typically 0.25 to 0.34 kg per meter cube, but preheated hydrogen can push this to 0.45 kg per meter cube, almost matching natural gas. But there are technological challenges. Injecting hydrogen cools the raceway and lowers the flame temperature, which can disrupt smelting. Hydrogen also causes a radial heat imbalance in the hearth, overheating the walls and underheating the center, potentially damaging refractories. Additionally, modeling results often differ due to poor simulation of the water gas shift reaction and hydrogen utilization pattern. That's why more validated trials are essential before large scale rollout. Still, hydrogen holds the highest potential for long term decarbonization, especially when combined with preheating and a small oxygen enrichment. Let's now bring everything together in a comparative summary. First, we have natural gas. It shows the highest coke replacement ratio up to 1.1 kg per cubic meter and meaningful CO2 reduction potential of up to 0.10% per meter cube. But its challenges include soot formation from unconverted methane and possible cooling of the Tuyeres zone. Coke oven gas, though more limited in volume, performs quite well. It provides around 0.4 to 0.49 kg per meter cube CRR, and its CO2 reduction is comparable to hydrogen thanks to its low carbon content. However, it competes with other in-plant uses and is not always available in surplus. Then comes hydrogen, both in cold and preheated forms. Cold hydrogen provides a moderate CRR of 0.25 to 0.34, but preheated hydrogen can push up to 0.45 kg per meter cube and deliver up to 33% CO2 reduction at the furnace level. The catch: preheating hydrogen is energy intensive and injection causes uneven thermal distribution, making modeling and control more complex. So while natural gas remains the most practical option today, preheated hydrogen shows the most promise for deep decarbonization in the long run if economic and safety barriers are overcome. So let's wrap this up with some key takeaways. First, fuel injection of hydrogen rich gases is a real and practical strategy for reducing CO2 emissions from blast furnaces. Natural gas, being mature and energy rich, gives the highest coke replacement ratio but require care to prevent soot and raft loss. Coke oven gas offers a good balance. It's clean, hydrogen rich, and well integrated into steelworks, but its availability is often limited. Coming to pure hydrogen, especially when preheated, has the greatest long-term potential with CO2 reduction as high as 33%, but it still faces hurdles in terms of infrastructure safety, and the biggest factor is cost. So modeling tools are improving, but we need more real-world validation to ensure industrial stability. As green hydrogen becomes more available and as carbon regulation tighten, hydrogenous gas injection could be game changer for steel decarbonization, especially in regions that still rely on blast furnace route. Thank you.